Okay,
Yep.
I'm gonna take. All right, awesome. So where we left off is last time we got pretty far along on interruption and resource safety. So we got to the point where we could interrupt things, we could control whether they were interruptible or not. And there's potentially like a little bit more we could do of building from there to implementing acquire release, which is kind of the fundamental operator for safe resource handling. But that's getting a little bit advanced. So we thought, as Kit said, it would be a good time to complete the Triforce. So the last type parameter that we're missing from ZIO right now is the environment type, the R type parameter. And that represents the services that our program or our workflow needs to run. So maybe we need a database, or we need a logging service, or we need Kafka. And the R lets us build a whole program that describes those services we need and wait until the very end to provide the actual implementations we're using, so that we can swap out different implementations if we want to, as well as we can just keep that logic very nicely separated. So I think if you've watched some of the other videos that Kid and I have done, this lets you encompass a lot of your logic in these different modules. So you're implementing this onion architecture idea of each module self-contained knows it's part of your logic of, if you're doing something with a GitHub API, you have some GitHub service that knows everything about how to work with the GitHub API, but it just knows about that layer. And maybe it's working on with a HTTP client that it doesn't know anything about GitHub, but it knows about making HTTP calls. And so the GitHub service relies on that and kind of translates that higher level, that lower level, just HTTP logic into this higher level GitHub API. And then your own program maybe translates that into an even higher level API of, you use that to get a bunch of metrics that you're going to display or things like that. So that's the idea of the environment type, but how do we actually implement it here? So we're going to follow a pretty similar process, I think, to what we did for the arrow type. So I think the plan is roughly going to be introduce type parameter, break all the things, fix all the compilation errors. Yay, pair coding with Kit. And then once we have that, we'll be at a point of, we could call it compiling, but not actually using type parameters. And then we're going to do the same thing we did with the arrow type, where we're going to think about what are the fundamental operators for introducing the type parameter and for eliminating it. So for the environment, the fundamental operator for introducing it is this one that we call access, or it's becoming more service in ZIO 2.0 with the way we're using has and layers, but it's basically, we call it access or service, and that says we've got something, we want to get something out of the environment. I want to get a database and do something with it. I want to get that GitHub service and do something with it. And then the other one is going to be what we call provide, which is like, okay, at the end of the program, we've actually got to give it a database service, or we've got to give it this GitHub service so that we can actually run our program. And so that's going to have a part where we're going to just call it introduce the operator, and then we're going to initially just implement in terms of new primitives. And then finally, we'll actually implement those primitives in the runtime. And then finally, we will we will actually do some examples. Does that sound like a plan? Oh, wow, that's cool. Got like a water gun and a clown. Nice.
Thank you. Introduce and eliminate, Yay. Yeah, it sounds great. It's a program for introducing the environment. Let's do it.
It is a program. Okay, so first thing, we're going to introduce this type parameter R here. And we're going to give this one a minus instead of the plus that the others have. And you can go back to another video we did about variance for more details on this, but the plus means that it's an output of this workflow. So when we run a ZIO program, we either get an error or we get a success value. And so it has a plus. It's kind of adding an error or success into the world. And the R is the opposite of that, that this is a input into our program. We need an R to run in something. We're kind of taking an R out of the world and we're consuming it and using it for our program. So we have a minus here. And once we do this, and I get things compiling, we're going to have many compilation errors because now everything has, ooh, I'm surprised by that. That's probably because I didn't save. There we go. There are my 66 compilation errors. Yay. So now we're going to go through, and this is like a little bit tedious. So this is why you try to ideally figure out how many type parameters you want early in the development of your data type. But we're going to go through and just add that extra type parameter to everything. And yeah, and generally our rule is going to be that if it's on the tray here, it's already got an R. And so unless it's doing something with the R, it'll just pass the R through unchanged. And generally when we are creating a constructor, unless it's specifically using the environment, we'll just use any to indicate that we don't require any environment. So like here, when we fork something, that's going to return a new ZIO that needs that R. Here, we're just going to pass through the R unchanged. For some of these where we are returning a new ZIO, we're going to do something similar to what we did with this A1 and A here. And we're going to do this R1 is a subtype of R. And then this is going to be an R1. And this is going to be an R1. And just like we talked about with the error type, what this is telling us is that this, like in this catch-all, we're catching any errors from the original effect, and then we're running this new workflow. And so this workflow, this new one, may require some services that are in addition to the ones that the original workflow required. So maybe our original one just required the database, but now this error handler also requires logging because it wants to log the error that occurred. So this new effect can use additional services beyond the ones that the original one did, which is why we have this R1 as a subtype of R. And whenever we're talking about the environment, subtype means you require more things. It's not enough that you just have a database, you have to have a database and logging. And so then the resulting effect is also going to require the database and logging instead of just the database. So I'm going to kind of follow that, and probably Kit's already done most of it by now, knowing him. But I'll try to at least do my part here. And some of these, like this one, doesn't work with the environment effect at all, so that'll just be R. Oh, wow, yep, look at him, he's already up here. Me. I think we're overlapping a little bit there. Okay. Yeah, I think we managed to step on ourselves a little bit there.
To which I guess failure is this then? There we go, yeah.
Okay. And then, okay, we got a few more. Okay, so now it looks like we're in the runtime here, and yeah, so we just basically added another type parameter. So we'll just add another one here.
Any.
Yay, forgetting types. Okay.
Oh, and above. And at the top of fiber context, do we give it an REA, start ZIO REA? Forget if that's correct.
I think we can just give this one a E. Yeah, I think that'll, and that, yeah, that can be any EA, or this is where if we want to, we can also add our lovely type aliases. So this is where like we would do, if we had a companion object here, we would do type IO EA is ZIO any EA. But right now I'll just comment that out. Okay, so now I think we're just about, maybe we have one or two more of these. Oh, that's a warning.
Oh, 3. Okay, yeah, so this needs a, I guess, so fiber does not have an R parameter, and so fiber context, I set it to on line 31 to say any. So that's a question I guess I have for you, which is, should fiber context have the R?
Yes, so I think what we're going to do is we'll say that when we run it, we have to have given it its environment. So let's see, this is in this unsafe run fiber method. So I think what we can probably do here is we could require implicit evidence that R is any. And then we can use that if we basically we'll need to implement an operator to use it. Right now, I think we can just do, knowing that we can do this as instance of ZIO any EA. And then I think this will be happy here. Okay. And then let's see.
Oh, then you have same with this. We'll have to just add the implicit evidence. Safe run sync.
Exactly. Okay.
And 102.
And
then, erase ZIO REA.
Oh, this is because the other two were covariant, so we could do this just by saying it. But this one, we actually have to kind of voluntarily forget this information that we require this thing.
Okay, and then one last error on line 90. Not found type R, so I think that would be any.
This any. Yeah, exactly.
Okay, and now we're not good.
Oh, we got some more. Yeah, exactly. Yeah. Oh, we're ready to have all of our examples not compile. Yay! So
good.
I think this, yeah, exactly. So I think this is why in some languages people are like, oh, don't add the types, because then it's easier to refactor, because they can mean anything you want.
We can delete them for most of these, actually.
We can. I think we'll just have this update.
Okay. Then for ZIO app, I guess we'll say any that we run. Okay, cool.
Yep.
Oh, and one more. A couple little ones.
Yep.
Okay. Very riveting.
All right. Well, that was very, very efficient for doing something. So let's try running a program and see what happens here. So maybe we can try our, like, what was it, par? Okay, so async began asynchronously, and we had woof, woof, woof.
The dog has found the result, yes.
Yay. Okay, so going back to our little agenda here, if I can find it, which maybe, oh, there it is. Okay, so we introduced the type parameter, we broke all the things, we fixed the compilation errors, we saw that we are compiling, but we're not actually using them. And now we need to actually start doing some things that are going to work with these operators. So the two fundamental operators are going to be, I think in this example, because we're not really using ZLayer and has here, maybe that can be the project for a future endeavor. The first fundamental one is going to be this one called access, or maybe we'll actually make the most fundamental one this access ZIO. And so this is going to have an REA, and it's going to let you use that R to do something else. And we'll just make this its own new primitive, kind of taking this idea of like, we're going to be as lazy as possible for a while, and we're not actually going to just kind of say what this does. We're going to just like add a new term to our primitives here that is going to cover this for us.
Mm-hmm.
And then the second one is going to be this operator called provide. And maybe that one we'll put on the trait. I think that'll be a little bit more intuitive here. Okay, we have that. And so provide is going to take an R and it's going to give us back a new ZIO that doesn't require any environment anymore. So if we go down to access here, this gives us an effect that actually requires the environment. This is the only, at this point, this is the only thing that actually introduces something that has an R. If we look at all the other constructors we have, they all return a ZIO that doesn't use an environment, or we have operators that maybe say if a ZIO does use an environment, then it's just like same environment. But this is the first one that introduces using the environment. And then provide does the opposite of, it takes something that uses the environment and it takes that away. So let's just implement at least these primitives here, and then we can see a quick example of that. So I'm going to go down here. We've got our other primitives. And so I'll do case class access.
Does that look about right?
Mm-hmm. Yep. So we've got our two new primitives here. And we'll come to how we implement them in a second. But first I will just make sure we are, provide is not a number. Oh, I think it's, is it new ZIO provide? Should be. Call something different, case class provide.
Are we in the object ZIO? Yeah. What?
Oh, maybe I need to save. That could be, there we
There
go. Okay. Yeah. Okay, so just with these, I could do a simple example. Where I could do something like I could say access int. And one of the things to note about this environment type is when you're accessing it, that's one of the few times where sometimes you will need to say what the type parameter is that you're like accessing, because you could theoretically be accessing anything in the world. You could be accessing an int, you could be accessing a database, you'd be accessing a logging service. So you often will need to tell the Scala compiler like what it is you're trying to access. Sometimes if this was like you were implementing a method and the method signature already said what you were using in the environment, then you might not need to, but don't be surprised if you need to add a type parameter here to say what it is you're accessing. So in a really simple example, we might say, well, access an int, and then just print out that int. And so if we look at that, and let's see this. Oh, in ZIO, we have some tricks that we use to only have to specify one type parameter here. But I don't have those tricks right now. So we will specify a few more type parameters, I believe. And then.
That definitely.
Oh, I called it access ZIO. That's
oh, I see.
Okay, so that's looking, we have some tricks in ZIO to not have to specify all these type parameters, but like just specify that one you're accessing. But we will save that for an exercise for another day. And if we add the type signature here, we can see that this is something that requires an int And then in this case is going to just produce unit because all it does is print it out. And I think sometimes the like requiring int, just like the environment, can be a little bit less intuitive for people because I think we're used to like working in forward logic flow, you could say. So we're kind of used to saying like, okay, I'm here and I need to go here and then here and then here and then this other place to get to my final destination. And this environment type works the opposite way, really, of like, it's the thing you need. And you can go from the thing you really need to something else that, well, if you have that thing, you get the thing you need, and you could work backwards from there. So you could say, well, like, if I need a logging service, then maybe my logging service itself needs a console. So, okay, I need a console for that. And you can, Kit's done all these like great videos where like the old lady needs the fly and all this great stuff. So that adds in this requirement for an int. And this you could think of as a program that we can't run yet. It needs this thing that we don't have. So it's like a car without gas. And the way we give it that gas is we do ZIO.provide. And so here I could do like 42. And so if I call this ZIO2, and I add the type here. So now I've made that int requirement go away. So now this we could think of as a program that's ready to be run. And I see Kit's setting up another good analogy for us. So you wanna walk through that?
Oh, sure, yeah. So I mean, it's just that this R parameter, you can think of it as sort of the requirements just as the arguments to a function are the requirements, right? When we define this method here, we can use int inside of it as though we had it, but we don't actually have an int. We're allowing ourselves to abstract over some context that has an int. But before we can ever run this method, we have to call it, right? We know this very well by now, I'm sure, defining and calling methods. And this environment parameter is sort of the exact same concept, just taken to the value level, which allows it to compose in all of these interesting ways. You don't actually have to type out your parameters every time. We'll see that next. We haven't done any composition here. I think it might work already, actually. But yeah, that's kind of a simple way of thinking about it. It's just, yeah, when you add an environmental dependency, you're kind of like adding something that's akin to a new parameter, if you think of parameters as requirements.
Yeah, I think that's a really good way to think about it. And a lot of what the environment type in ZIO does is it lets us plumb these things around in an easier way, where if you wanted to, you could just do everything as methods like this. But you get to this point where maybe all your methods are going to have 20 different parameters because you got to pass around your Redis and your Cassandra and 20 other things, versus this makes it easier to bundle all of that up for you and pass that around, and you can get it when you need it, but you don't have to write 20 different parameters to every method. And it's also exactly right that another thing we can do here is we can already see how these can start to compose. So I could do another method here that's like, I'll just grab this. And this time, instead of accessing an int, I'll access a string. And maybe I'll print something. I'll say, look, I'm a string. And if I add the type parameter this, I see this needs a string. And then if I put two of these things together, I can add so much beauty to the world.
Oh, can you add the type signature to ZIO4? I don't have that power.
So oh, yeah.
I mean, I
have the power.
But just to prove that we're not lying.
Yeah.
Yay. So this is what you cannot get with just normal methods, right? If I had a method that needed an int and a method string that needed a string, there's no way of saying like method 2 is method and method string and then like automatically joins their types together. No, like we'd have to manually do this ourselves, right? Write the boilerplate, which is fine. But in a large application with lots of dependencies, this ends up being a lot of code, and it kind of makes it hard to refactor things if you want to change your not like that. It would be a method and meth, if I can spell, method and method string. I mean, and this would also have to be on 2 lines, right? Because we don't have any other sort of composition or operators. But that's kind of the idea, is that this is the equivalent. However, here we just zip 2 methods, and we can just generate the types, and it'll do that work for us. And before we call ZIO4, we obviously have to provide, well, this is where has comes in, which we haven't implemented yet, but this is where the wrinkle exists that will motivate this new data type. Is that if you imagine a ZIO5 that we want to provide to our ZIO4, well, what do we need to give it here? We need to give it an int width string. And unfortunately, that is not a type. So this is why we need to come up with some other magical thing that will look like this eventually, that we can construct out of individual values. So yeah, you can see where the potential power is, but we need this other abstraction. But well, let's forget about this for now, so we can look at how it's implemented, because this doesn't change how the environment itself is implemented. That's just a layer of complexity atop for dealing with certain necessities.
Yeah, exactly. So we will get there, but first we just got to get this working at all. And so where we're at right now is we've kind of written the check of, we've said, okay, we have these operators, but we haven't interpreted them yet. So that's the next thing we need to do, is we need to go up to the run loop here, and we need to actually say how these are going to be executed. And so we're going to have these 2 new things. So we're going to have, yeah, we need the ZIO, so we'll call ZIO dot access. And then we'll just call this F. And we have provide. And so when we introduce these new types, a lot of times what we need to do is we also need to introduce some new state that we're going to need to track within the run loop to use this. And that's one of the nice things of having this run loop, is we have one place to do all of that. And so here, I think there are a couple of ways it can be implemented, but I think maybe the easiest way to do it here is going to be to think about the environment as a stack. So you could say initially when we run our program, we have no stack, or maybe we have one thing in the stack that's just the unit value, that's just an environment that doesn't give you any capabilities. And then as you go along, whenever we provide something, we're going to put something on to that stack of environments that we can access. And for the duration of whatever thing we're providing to, that thing is going to be the environment we have. And then this access method is just going to let us look at that thing and grab it and do something with it. And so we're going to be able to use some of the same operators that we used before. And working with the stack, we're just going to have an additional stack. In addition to having that continuation stack, we're going to have an environment stack. So let's start by creating that for ourselves. So I'm going to go up here, and why don't we say environment stack is going to be another stack. And this one's going to be a stack of any, because the environment could theoretically be anything. It could be an int, it could be a string, it could be a has database, it could be any of these things. So we're going to just have any for the environment type here. And then accessing the environment is going to be pretty simple if we have the stack, because we could just say something like current environment is equal to environment stack dot, I think we can peek, is that a thing we can do? I guess we can just do head. And so notice here, there's a little bit of unsafety and a responsibility we're taking on here of, we're saying, we're going to make sure that if anyone ever calls this and runs this program, that there actually is something on the environment stack for them to get. And so like, that's one of the things we were enforcing with that implicit evidence to run the program of, we said, Well, if you have an environment in your program that hasn't been provided, you can't run it yet. And so if you've tried to access something and you have an access, but you haven't provided it, then you're not actually going to be able to run the program. The only way you're going to be able to run the program is by using this provide thing, which is going to put something on the stack to make sure that it's there for us to get. So in access here, we can get the top thing off the stack. And then remember, this f here is a function that's going to take, it's typed as any, but that's supposed to be the environment. And if we give it the environment, it's going to give us back a new ZIO effect. And so here we could just say, current ZIO is equal to f of current environment.
Nice.
And so the other side of it is providing it. And so this has one part of it that's really basic, and then one part of it that is just a little bit more complicated. So the basic part is we've got this environment here, and we need to put it onto the stack. So we could say environment stack.push env, and that'll make sure that by the time we get to the access, we're going to have that. So we won't cause a blow up for ourselves here. And then another pretty clear thing we need to do is we have this inner ZIO inside. So we need to execute this because this is the thing that's expecting the environment. And so this is like, I guess, the most naive, but there's one thing we're missing here, which is right now we're going to put this onto the stack, but we're never going to take it off of the stack. And there we go. Yeah. If we think about like how a user might write their program, they might do something like they might do ZIO1 dot provide 42, and then they might do like star right ZIO2 dot provide 34, and then they might do ZIO3. And so if we don't do anything else here, if we just, well, if we comment out what Kit so wonderfully added, then we are going to run into a problem where this first ZIO is going to run with 42, which, okay, that makes sense. Second one is going to push something else on the stack. So the stack will be 42, 34. And the second thing will run with 34. So that's fine. But then we're going to get to this ZIO3 here, and it's just going to still have the 34 sitting on the stack. So if it tries to do something else, it's potentially going to like have this thing and be able to do something with it. Whereas this 34 should really be local to this effect. It shouldn't be available to anything else. And so this is exactly what Kit added with this ensuring operator. And that is going to say, okay, as soon as, so we're going to push this on the stack. And then as soon as we're done running it, we're going to pop it off the stack. And this is also a nice example of how, as we build this out, we're able to reuse more of our own operators. Because if we didn't have this ensuring thing, this logic of like how we pop off this environment within this recursive execution of this run loop with these other continuations, it wouldn't necessarily be completely clear. But this ensuring operator, basically, its like job is to do this thing. And so just like when we were working with interruption last time, and you can see we had something really similar here where we changed the interrupt status and then we used ensuring to put it back to its old value when we were done. And we're essentially doing the same thing here. And in a way, it's even easier because we've just got this stack. So all we have to do to restore is just have to pop off the last thing. We don't even have to go through like getting the old one and saving it and restoring it, though that's the other way we could implement this.
Sure.
So I think modulo, we may have made some bug and maybe about to blow ourselves up here. I think we have what we need. If we go back here,
I should run the example. I imported the ZIO
oh, perfect.
App type into this. If we go to the object we made below.
Oh, yeah.
File, yeah.
This one here. Okay, great. Let's.
Where do we have the?
check
But I think we need
ourselves.
to extend it on our an example. One sec. So extends ZIO app, and then I will do def run. Oops. Def run equals ZIO2, right? This is the one that we're providing, number 42. If you want to go to line
Yeah, where should I go to?
415.
415. Got it. Okay.
Cool. So I'm running that one currently.
Okay.
Should look for example. This is probably like 2 or 1.
It's 1. Okay.
So yeah, printed out success, or printed out 42 rather.
Yeah.
So that's what we wanted to do. So we ran line 412 then. Cool.
Yeah. So that's pretty cool that we were able to, I mean, probably a little over half an hour able to add the environment type here.
And I guess maybe in order to explore the thing that could have been like that bad, potentially bad case.
Yeah.
Scary.
And make sure we haven't actually accidentally done it. Yeah.
So yield whatever X. So let's say, oh, and this might actually be another way that I often use the environment is like, you can just use it directly, right? So X could be ZIO.environment int, right? So if we wanted to implement this, if I can, I'll summon the to my side. I think this will work. So this is very similar to access, except this would just be called environment. And we don't need it. We just needed we're just really one parameter. And this is, I guess, going to be R. And doesn't take any arguments. And it just basically creates an effect that's going to not fail, require, and return the thing. So it's basically access that's just taking that environment and doing ZIO.succeed. Oh yeah, gotcha. .access ZIO, returning it, right?
Yeah.
So,
and this is another example of that pattern we talked about when we were doing fold with the error types of how you have that one most primitive operator, or 2 in case of the introduction elimination, and then you can use it to implement these others that end up being more ergonomic for a lot of common cases.
Yep. Okay, so coming back down to this bit of code. So now I can get an int out, but then I can also have some y, which might be that first ZIO. And to this I can provide something, right? So I could provide 42 just as we were before here. I could run this for its side effect. And then whatever, let's do y again. It's going to be the same number both times because we're not providing it anywhere. And so if we did this, potentially a scary case, and provide 100, we should see in between 42 get printed out, and finally we should get back 200 as our result. So let's maybe run that. So it's 1 still, I hope. So yeah, 42, and then we got 200. However, if we go back to our run loop and forget to pop it off of the stack, our little ensuring here, if we comment this out and now run it, we're actually going to probably get 142 as our final result, if you can run that. Yeah, and the reason why is because, so this is the case where it can be really tricky, because we're pushing at the very top, basically at like line 428, you can imagine, if this gets turned into a succession of flat maps. We're providing the 100. 100 is our stack. Then we get to this provide, which will push 42 onto our stack. And then this one is never, and then once this exits and we get down to this third statement, 42 has not been popped off the stack. So when this goes to access the environment, it's still going to be 42. So that's sort of a great case for popping it off the stack. So I will undo my comment there. So it works as expected. But yeah, that's great. It works. Yay.
Yeah, another thing we could try if we wanted to is we could try doing a failure within the environment usage and show that gets restored, because that's another thing that ensuring operator buys us, is that if we even if we fail, we still do the popping.
Oh, sure. So that would be like if ZIO did like a ZIO.fail, oh no. And then maybe we could do catch all ZIO.succeed of unit. So we're going to fail in here, which theoretically won't be caught until this. However, because of exactly what you said, that ensuring being part of the way provide works, it's It's not going to just jump right to this catch-all first. It's going to pop off of the environment stack. So we should still see the right answer if you run this. Yay.
Yeah, yeah, exactly. I feel like it's almost like 95% confidence here because it's like, is this where we made a mistake?
But no, we made it.
Yeah.
So do we want to, is there anything else you want to talk about, just the environment as is, or if there are any questions in Discord, feel free to ask those. Oh, actually, this is great. So Francis asked a question about 10 minutes ago. Sorry, Francis.
Oh, sorry about that.
We might still be on the same topic, which is I've attempted to implement this a couple of times and wonder, is there any way to implement this in a completely type-safe way? Do we really care, or are we okay to be a bit dynamic at this level? So I'm assuming you're talking about sort of the whole run loop, or maybe the environment in particular, just due to all the any's. Yeah. Yeah. So I'll let you get that, Adam. I'm sure you have a lot of thoughts on that.
I think if you really wanted to do an exercise in like GADTs, you could potentially do something there. You could imagine having a GADT where, and sorry for folks, that's what's called a generalized algebraic data type. And so what it means, it's like a nested data structure where you have different types at different levels of the structure. So like instead of like a list of ints, like every time you go in and you look at like the cons case, it's like more ints. It's always a list of ints. This would be something where at first you look at it as an int, but then the next level you go into it's a string, and the next level you go into it's a Boolean, and it's all sorts of things. And so it's a little bit more like the H list or the H set that we worked through in one of our videos on type level programming. And I think if you like really like pushed on that and like that was what you wanted to do, that could be an achievable goal. But I think you're going to do it at a significant cost to performance, because you're going to be building this whole data structure that's kind of optimized for maintaining the types at each level, versus like the underlying implementation of this stack is basically just going to be like one flat array that gets resized at a certain point if it gets too big. And I think the value is also limited here, where this unsafety is only part of the internal API. It's not something that we're exposing to our users. By the nature of the way we've defined this access and provide, and the fact that you can only run it if the environment type is any, the API the users have is type safe. So I think this is a case where, even though maybe you could, your time's a lot better spent adding additional features and functionality and performance to this than making this type safe. You're better off just accepting this is where you're gonna suck all the ugliness of the world and handle it so that other people don't have to deal with it.
Yeah, I agree. I think that's always a struggle, especially, well, I don't know if especially, but when I was first getting really into type safety and generalized algebraic data types and all this kind of stuff, like it takes a while to get a sense of where type safety ends, like between runtime and compile time, and really getting a handle on what you can bring with you across that that membrane onto the other side. And it's often less than you want, like because you're used to all this type safety in a certain context and you want to have it everywhere. But really what we're doing here, like we don't know how many times we're going to go through this loop, right? There's just a stack of any's and we don't know how big that's going to grow. You could, as Adam's saying, like build a type that is sort of represents at the type level your entire nested program, but that is going to look really horrible as well. Even beyond the performance downsides, there might just be, it might actually be too painful to carry all that type information around. Yeah. But maybe some people appreciate it. Cool. And exactly, so then Francis said, so then it goes back to the test versus types debate, and I guess tests are perfect for cases when things become dynamic, yeah. And this is kind of the other benefit of this, is that we have a run loop, which is super dynamic and crazy, but it's only right now like, it's 80 lines long. Maybe the whole fiber context, maybe 100 lines long. So it's really a small proportion of most of the code. Most of it is written in terms of higher level combinators, that all sort of desugar down into this really tight, thought out set of primitives. And those primitives are what we sort of deal with in this crazy low level way. But if we can ensure the safety of this by testing the living heck out of the run loop, then we're pretty confident that we can extend onto this and that these laws will compose, these little properties will compose as our applications grow more complicated. So yeah, testing is definitely good for this stuff.
Yeah, and that means our users should still do tests because types are not actually a substitute for tests, but it means that the users can still rely on those types.
Yeah. Cool. So
awesome.
with that, shall we check out the has? I think we talked briefly about the motivation. We can explore.
I can has, and so can you.
Exactly. Yes. And I have done a small video on this topic before, but it would be good to sort of tie it into the actual runtime now that we're implementing this and see how it all relates to one another. So now we know what the environment is, we know how it works, we know that it's actually pretty simple. It's really just an abstract way of passing parameters around. And it has this nice property, as we've seen here, which gives two ZIO effects, and I can just give these slightly different names. So if we have an, oh, if I can, never mind, my shortcut isn't working. Do I have rename symbol? Rename symbol, int ZIO. Yeah, so we have an int ZIO here. So this is a ZIO that requires an int. And then also, we can have ourselves a string ZIO, which is going to be a ZIO that requires a string. And then this one, when we combine them together, and notice how we don't need to annotate this, we could just have IntelliJ or VS Code even, now these days, insert a type annotation, except I can't do it, only Adam has to do it. My fault, Adam. Well, I'll undo this. Oh,
no.
You got it.
I can add some value to this part of the presentation.
Thank you. I guess certain powers are beyond the live share. Well, yeah, imagine if I had powers to type annotate anything, the chaos. Int string ZIO. So yeah, so this is the combination. And this is just because we're sort of piggybacking on a feature of the Scala language by making this thing contravariant, the little minus R sign, by making the parameter contravariant, and by, in our definition of zip, it looked like, zip that, some other ZIO, except that other ZIO's environment was a different type. It was this R1, which was more specific than our R in context. And this little bit right here is what allows the Scala type system to come up with this new type here. It basically is going to with together the initial type with the other type. And if they're the same, it'll sort of like erase that. So if they both required ints, it would just say int. And it could do this multiple times. If there was already an intersection type, it's basically doing the set union of these types, which is really convenient because we can keep zipping along different ZIOs with different requirements, and we just get it summarized for us for free, which is super nice when you have a huge application. You can just kind of like regenerate these type descriptions and you don't really have to type anything. It's quite nice. It's a lot more painful to sort of have to change how you're threading parameters around everywhere. Cool. So that's nice. The problem is this is nonsensical. The problem is that now what we want to do in order to call this method that's going to run both of these operators, look, I'm a string and print out this int. The problem is that we have to provide this nonsensical type called int with string. And we can't do that. We can provide a string, but this is an int, which is going to yell at us saying, you need an int with string. And we could try to, in vain, provide a string, but no, this is not an int any longer. And you can't really create one that's a subtype of this. These aren't traits. One solution would be to, instead of doing this, use traits. So I can make a trait called like has int or something, if you will, that might have an int inside of it. And then another one called has string. And so instead of relying on int and string directly, I can instead rely on has int and has string. And then I can, access in here the int. And in here I can access the string. So that would work. And if I regenerated this, it would say, I want to force Adam to do that again. It would do this. And now what we can do is we can make a new has int with has string, because that's possible to do with traits. We can create a new instance that conforms to multiple traits, even though I should give these the proper types here. So that's a string. So now here I need to say like, def or val, I guess I should have made those defs above, but whatever. Val int equals 42 and val string equals hello. And theoretically, this should now compile. Could we run this?
Mm-hmm.
So yeah, we got both results out, 42 and look, I'm a hello.
Hello.
And then we got the two results of these, which were both units. So not terribly exciting here, but those are the results. So this works. And this was actually sort of, correct me if I'm wrong, Adam, but I believe when I first joined ZIO, this was kind of, when I first learned about ZIO, this was the recommended way of dealing with the environment with some additional bit of recommendation in terms of the pattern. But this was kind of it, because you could see how it's the next easiest solution to that problem. Oh, you can't make an int in a string, but you can combine these. And we could think as to what are, and then console.
Yeah, you could have something like console, and then you would have this other thing. This would have like its own thing. Val service, console.service.
But I think even though, wouldn't it have to have sort of a special name here? Because I think this is kind of one of the issues with this, is that because at the end of the day, we're combining these, there's a bit of a naming collision issue, right? Whereas if I had another service here, right, trait database.
Yeah, exactly. Yeah,
it would have to be called, database.
Right, right. This would be like console, and then you would do like object console trait service, and then this would be like.
And this is sort of the beginning of that service pattern. This is why that service came in.
Exactly.
We were eventually able to remove that because has gives you some other ways of dealing with this. But this is kind of like, okay, we want to be able to use this. This is a great power. This is super cool to have. The one problem is you can't just use traits directly, because then they're going to have all this namespace issues. If it was just console and database here, what if they both had like a notion of get or something? Then you couldn't implement both of those traits if their methods overlap. So you have to separate them out by maybe tucking the actual trait into some nested trait, and then you only have to worry about sort of a smaller service area of potential overlap. There is still a service area of overlap, so you'd have to be careful, and you might have to rewrite your traits in certain cases, and that would be very painful. And so this is not the ideal solution. It would be nice if you didn't have to work in this way. Sorry?
Oh, no, I was just gonna say, if you thought this was like a little bit boilerplatey, imagine you had 20 different services. So even with this like def console thing that kind of bundles them up a little bit for you, every time you do this, you have like 20 different things you're listing. So that gets really boilerplatey. And then what this doesn't let you do at all is work with an environment type that's abstract, where you just say like, well, it's R with console. You don't have any way to work with that R. You can only work with a set of concrete types. So there were a lot of limitations with that.
Yeah, I could also imagine that. So like here I've made the myEnv type, right, which is this. But what if I wanted to use this in one piece of the code, but then also elsewhere I needed also to have console, right? There's no good way of really like taking this definition of the environment and, combining it with some magical operator with an instance of like the console type that we don't have right now. But like, how would we join these together? Basically, we'd have to sort of like build a whole other one of these environments every time. So it becomes repetitious and painful. Many downsides. We don't need to get into the whole history, but that's kind of why this is kind of why we end up where we're about to go, which is that, we want to be able to use this contravariant set union capabilities, which makes it super, like there's something really nice here, is that we just get to zip together all of our requirements almost for free and just auto generate the code. Like it knows that even if you don't, even if we don't give this a type annotation, it'll still know it, right? It'll give us errors. We could use the types there for macros as we do now currently with the ZIO magic stuff and what's in ZIO 2. It gives us a lot of power. But how do we fix the issues that we just described? Well, we kind of want to move. We can't just do this. We can't just do int with string. No bueno. But we would like something where we can basically define each bit in isolation. So some int, the int environment, right, which would have some definition that would give us the int. And then separately, we can define like a string environment that would give us a string. And then later on, we can take these two environments and add them together. So they can be defined separately from each other and composed and provided and accessed in the same way, and maybe even in a more uniform way. So instead of having to define these different non-overlapping namespaces for actually getting the value out, it could be a little more uniform and a little less special casey. And this is where we have this type called has. This sort of magical type called has. And let us just first do the types. So I'm going to delete this. So we're going to get rid of these things. So we're going to have has int and has string. And obviously, has int is not an int. So we need to get the int out of the has. And it turns out that this environment, this has a get method that we'll have to implement. And this will just get us the value that it's parameterized by. Pull it out of this environment. So I could say end.get string. And so that's going to get us a string. This is going to get us an int. So it's already a little more uniform. And we want to have this capability of being able to compose these together to get the right environment. And my end will clearly have to be actually, because what it requires down here is going to be a ZIO of has int with has string, nothing units. So by combining these int n plus string n, we're going to get has string with has int. And this should fulfill these environments. It should fulfill that type signature. And amazing, already stubbing out the implementation. So let us see, why is it sad? Oh yeah, I need to change this stuff. Has int and has string. And why is this sad? Required has int with has string. Oh, nothing, oh, yeah, a tuple of units, because that's super useful. Okay, so yeah, this is kind of the aspirational API. And as we can see, just from using it, it's way better than the thing that we had before, because we can define these separately. And in fact, let me also add some more aspirational API bits. So I'm going to have a def succeed that's going to get us, that's going to take a value of type A, and this will return back a has of A for us. So we can do has.succeed of 42 and has.succeed of hello. Okay, so this code theoretically should execute once we're done implementing all the methods we need to implement. But there's certainly some strange things about this. Usually, when we make combinators, you don't get back an intersection type. That's definitely, I'd say, probably the strangest thing about this. Usually, you have some traits, some box of type A, like even, for instance, a ZIO, right? Let's just use a ZIO. We already have a ZIO. So you have a ZIO succeed of an int and another ZIO succeed of a string. What type are we going to get back if we do ZIO.zip ZIO2? Adam, can you do the honors of fulfilling that type information?
Mm-hmm.
So it's going to be a suspense, a tuple, right? We tuple up the values. So we're going to have we have a ZIO of a string and a ZIO of an int, and we get back not a ZIO int with ZIO string, right? That's not really a usual thing. However, yeah, we do not get this back. That would be weird. But it turns out this is where all the power comes from. This allows us to do some fancy things. This is what is the other side of the fact that when we use contravariants, this is the type we get. So we need sort of a combinator that gives us the same shape, such that we can fill it in. We kind of need the inverse of that, so we can compose and decompose with the same mechanism. So how are we going to do this? Well, let's take a thought. It turns out that, well, maybe we should actually take a slight step back first, because we haven't really implemented anything of has yet. But keep that in mind, that we're going to do something a little wacky. But before we even get there, I think we can just implement this example, or part of it. So what is a has? Right now I just made it a trait, but I can actually make it a case class or a class. But I don't know, I just go to case classes all the time. And what this is going to contain inside of it is a map. I often explain, is really just a map from types, like semantically, it's a map from types to implementations of those types. So you could imagine something like this being, like the literal string going to some string, and then the literal type string int going to that. So when you access at a given type, you're going to get back a value of that type. That's theoretically what it is. That's kind of exactly what it is, with a couple of details on top of it. These aren't directly strings, but we're going to have the keys as some kind of value you can access a map with. And the implementation is very much going to be a map. So we're going to make it, in this case, a map from, yes, string to any, once again. And this is also like the run loop. Unsafe internally, yet correct by construction. As long as we implement everything in the right way, we're going to expose an API that, if the user only uses that exposed API, which they should, and don't typecast anything in crazy ways, the API should always get them a valid result. So yeah, we're going to have this map inside. Missing implementation for get. Yes, of course. So how does this work? Well, when we call get, we actually specify. So let's take a look at like one way of using myEnv would be to say myEnv dot get int, and this should get us back an int, right? When we called get up here on line 411, we didn't need to specify the type because our has only had one type in it, so you can get away with that there. But if it has multiple types in it, like myEnv does, you can sort of specify the type is the key, just like in this map that we had, this map example. We would basically instead say map, there's no get. I guess there is actually a get, but that returns an option. Whereas this doesn't need to return an option because it's the type represents what's inside the map, which is the magic of the whole thing. But yeah, this is basically the same thing. We would get an int back, even though it would be an any in our API, any, which is an int. In our API, we get to, actually it's going to be an option of any. But in ours, we get back the int because we know it's there because it's in the type. That's the whole point of this magic. So in order to do this, we can call get on has. The one problem, though, is that here we have to think about what is a, right? Because a is string here, but it's int here, and our type myEnv is actually this intersection type that is both types inside of it. So that might be a little weird. In fact, there's no has that has multiple types in it at all. So how would we even really implement get here? It doesn't really make a lot of sense so far. Let's not worry about get just yet. We can do plus plus, sort of, because we just have these maps. So what do? Well, we need to make a has. We need to return a has that has both of the maps essentially just fused. So we can do this map plus that map, and then we might have to cast it to cast its type to this type. So we're kind of just lying. We're using the intersection type to just track some type information for us, and making sure that it'll work as it needs to. But it's kind of magical. Does this compile at all, Adam?
Let's try. I think we're.
Oh, I think I removed get. So that will not work.
Okay.
Let's try that one more. Oh, yes. Yeah, so then we need.
Yeah. So I got one more missing implementation for get.
Okay,
we're good. Yeah.
Okay, so we have plus plus, and theoretically this should work. Now we need succeed. So how should succeed work? Well, we could just make a new map, and we need to make a map that has some string representation of this type of this value, and we could do this by using the built-in Scala class called the what was it called again? Class tag.
Well, class tag and type tag. Yeah.
Yeah. So, or do I want a type tag? Right. One type tag.
They should work fine for both. Work fine for this. If you want parameterized types, like you want a list of int to be different than a list of string, then you want a type tag. If you just want to distinguish int and string, then class tag is fine.
Okay, let's go for the more powerful one.
Power.
I probably need to import this. So we can just, Scala will magically give us a type tag for the type of A. I believe. Not found value type tag. I just need it in. Can you import that? I'm not sure exactly.
Yeah, I think it's Scala dot reflect dot. I think that type tag.
Is that happy?
Seems like.
Maybe it's class tag. Oh, there's class tag. Okay.
Class tag is definitely in reflect. Yeah, I think maybe you need to do something slightly different for type tag.
All right, but this will work for our purposes here.
Definitely.
And then we can just take the class tag and turn it into a string. We just serialize it. So we're getting this value that represents the class of type A, and we can use that as the key, but just by stringifying it, because it's always going to be, maybe it'll be like scala.predef.string, but so be it. That's always going to be the same value, and we can use that as a string to represent a string and access it. So theoretically, that should work. Okay. Let's just do a has example. I'm going to just extends main real quick, or extends app real quick, and pull this stuff down here. And could you do run main? And can you make this like auto recompile to do the tilde run main on this?
Yeah.
I think it should be tilde run main. What was it? What is this file called? ZIO dot has example.
Okay.
Yay. Okay, cool.
Yeah, okay.
So we see the results down here. We can totally construct these values now. We get this, and it's very much almost identical to the type here, except yeah, it's java.lang.string is the serialized version of the class tag for string. But it sort of works. We can construct this thing, and we can combine them, kinda, because there's one other issue, which is if we had another has of a Boolean, perhaps, and we tried to also do plus boolean, could you generate the type on my end again?
Yep.
Ah! Something horrible has happened, and that I'll delete that, and that's okay. The reason why something horrible happened is because if we look at where plus lives, it lives on a has of A, and when we join it, we're casting it to a has of A with a has of B, which is great for the case where we're just combining a singleton has with another singleton has. But the second that gets bigger, it's like when we call plus on something that's already an intersection type, what is the A anymore? Aren't there there two A's, right? So how do you even operate on that? And this is where sort of the magic trick of has comes in, which will allow us to implement get and everything else, and just make the whole thing make a whole lot more sense, which is instead of operating on a single has, we actually do want to operate on the intersection type itself using the power of implicit extension methods. So we're going to have an implicit class called, let's just call it has ops, which will take some type, which is a subtype of a has. So some kind of has. And then self is going to be self here, being a little clever. So we're adding extension methods to any subtype of has. And what's a subtype of has? Well, an intersection that includes has is going to be a subtype of has. So has A with has B is a subtype of has in Scala. Who knew? It's kind of hacky, but it works out to be quite elegant in the end. So we can actually take this plus and put it up here. And what if also the left-hand side, sorry, the right-hand side is not a singleton has, but also already an intersection type? Well, so we're going to actually have a that, which is also a subtype of has. And what do we get back instead is going to be self with that. So this is actually what it's going to be. There's a little error here. Could not find value map yet, because now we have to say self.map plus that.map. And let's see what else it's sad about. Okay, and there's no end.get anymore. Okay, so that's one piece of the puzzle is plus. But for get is actually now possible to write, because get needs to be parameterized by the type that you're looking up, what you want. And what do you get back? You get back the A. As long as self includes that A, right? We don't want to be able to, we can't say Boolean if the has does not include that. And we can use the power of this subtyping and intersection types to have some evidence here. So we could say implicit evidence such that has of A is a subtype of self. So self, it might have to be the other way around. It's gonna be a little confusing. I think maybe it does have to be the other way around, where self has to be a subtype of has of A. So the thing that we're calling get on has to at least include has of A. So if it's has of int with has of string, then we can indeed call .get string on this, because this type is a subtype of string. Is of has of string. But we could not call has of Boolean. We're going to get a compile time error, which is another very lovely benefit of this. Okay, and in terms of the implementation, we just need one other bit, which is that implicit class tag again, a class tag of A, such that we can look things up in the same way that we put them in there in the first place. And this is pretty simple. We just do self.map and then access class tag.toString, right? Because that's how we put the value in there in the first place. And then it thinks it's an any, so we have to do as instance of A. And that should be good if I've written it correctly. Okay. So has is actually pretty simple. It's just this map thing. All the operations, or many of the operations, are on the ops, because we need to interact with intersections of these. So it's not your standard Scala. It's all a little bit more magical. So now, could you try regenerating that?
Yeah.
Yay! So now we can print it out, but then we can also try to get some values out. Let's try to get the int. Let's try to get the string, and then let's see what happens if we try to get a Boolean out of this. Oh wait, and then
this one has a Boolean. You may want to.
yeah, a double. There we go. And I see already that it says, yeah, cannot prove that has int with has string with has Boolean is a subtype of has double. And we can give that a better error message here by using that sort of implicit not found thing. No, or whatever. I forget where we have to put that for this to work. Maybe we could put this exactly in there.
I think it should be fine there. I think we're on 213. I think it's 212 for it's a little bit more.
Maybe I should put it directly above this implicit found no. Anyway, the point is we could, if we wanted to, also give that a nice error message. We will not for now. But if we actually run this by removing the thing that doesn't compile.
42, low, true.
Yeah. So now we have all the power of this ugly map, except we know what's in our map. We can add to it. And it just kind of works beautifully. And so now we can return above slightly to our example here. And let's see what we have. So now we can provide this thing. So now can you run the other example? So we haven't really changed anything in sort of in the run loop, but we've built this extra data type that works, that sort of interacts quite flawlessly with the environment capabilities that we've provided. We just have to change our type parameters, and we have to use this data structure, and then it just ran. Same as before, but now we have the ability to sort of define the pieces of our environment separately from one another. And they can have all the complexity that they need inside. And instead of int and string, this would probably be eventually like a trait like, console. So I could say def print line, and this could, be a ZIO of any nothing units, and take a message string, and then we can, okay, so we need to have an instance of this that we want. And, we can actually kind of just follow this pattern now if we wanted to. We don't have layers yet, but we can have a definition of this. So this n, we'll call it for now. We basically just want to do has succeed of a new console. And we can define a version of this, like this could be our live console. That's going to do ZIO.succeed, print line, message. So here, I could also combine our final int string ZIO thing. I could zip this with calling, this would have to be ZIO.environment. Well, here's the last constructor I will add, which is going to be, where is ZIO.environment, def environment. So up here, why can't I jump up there? Seems to be pulling me back down. Wretched. Okay, I made it.
Yeah.
So instead, we're going to have service.
Yeah.
And this is basically going to get us, it's going to look almost like environment, except it's going to require a has of R. So the only thing we need to do is just call .get at the end there, which is going to pull it out of the environment. Oh, and of course, we need a, due to our,
Class tag.
I need a class tag, which in real ZIO is this other type called a tag, which is more powerful and handles all those other advanced situations. Oh, thank you. Scala.reflect.class tag. Perfect. Oh, and R. Good. Now it's happy. So now we can do things like .service, and I can grab this console, and then I can flat map over it and call print line on it using my special message. Okay, so a pretty ugly effect. And it's going to give us a compile error saying that, okay, you haven't given us the full environments. We have string and int, but we need string and int in console. So now we can just do ++ with console.live to generate the full has. And now if we run this, we should see everything. And so now we have sort of the beginnings of this ability to compose our entire environment and swap in a live implementation for like a dummy implementation that always prints out, you know, the same dumb message called wowies. So yeah, we can kind of build these things incrementally, compose them. We get type safety. It's kind of elegant, and it's not quite, doesn't have the full power of Z layers, but Z layer is really just another layer on top of has with ZIO and Z managed, which is another type we haven't gotten to yet. It'll probably be in some future lesson. But yeah, it's this confluence of all these crazy ideas, and each bit, I hope you're noticing, doesn't really require everything else to change, right? It's sort of the beauty of composition. We're building one little data type that does one little thing. We're fitting into some larger system, and the total is greater than the sum of its parts, right? The gestalt is quite potent. And anyway, this is why we have this sort of environment pattern today, and the service pattern sort of falling out of that. So that was a bit of a ZIO history lesson, and I hope that was interesting. So definitely a weird tactic, but a super powerful data type, and a super, yeah, it works way more elegantly than the sort of the hackiness of its implementation might lead you to believe. But yeah, any did I touch on everything? I know we're almost out of time, but if there are any questions, feel free to ask those.
Yeah, I thought that was fantastic.
Cool. Woo! That was a whirlwind. We did a lot today.
I know. You know, I feel like we got a lot out of those, like the time after the hour.
The final 30 minutes. Cool. Well, I see Francis typing, but other than that, well, I don't know. Maybe this is going to be a huge question and send us off. Oh, no, that was great. We'll definitely watch this again. Live? Yes. It was good having your energy.
Yay. Yeah, it was great having you here.
Thanks for joining us today.
Yeah, more questions are great. Yeah, I'd love to keep it interactive.
But yeah, everyone, thanks for joining us, and
yeah,
see you next Friday for some more something else. Who knows?
Yeah.
We might switch off of ZIO for a while, but also we're open to suggestions. So yeah, hit us up.
Yeah. Have a wonderful weekend, everyone.
Yeah. Bye, everybody.